Good morning and welcome. This is Mark Richardson with Vibrant Technology, and we welcome you all to another MEscope ODS webinar. And today's topic, we're doing part 2 of using a cell phone video and ODS correlation to diagnose unbalance in rotating machinery. That is a mouthful. But hopefully those of you that are joining us got a chance to, were joined us last month for part 1. We are going to go over a few little summary type slides from last month, so we can bring you up to speed to where you are. If you also had a chance, you can go out to our YouTube site. We did upload part 1, so at the tail end of this, you can go and view part 1, and then early part of next week, we'll have this webinar loaded up on our YouTube site as well. So we are recording today. Everybody will be on mute for the duration of the call, and at the tail end of the webinar today, we will answer your questions. During the webinar, feel free to type your questions into the GoToWebinar panel there on the right side of your screen, and we'll get those questions answered. I'm joined by my father, Mark Richardson Sr., President, CEO of Vibrant Technology, and he will be going through the webinar today. With that, let me just hand things over. We'll get going. We got a lot to get to. Take it away, Dad.
Okay, thanks, Mark. Welcome to all of you. Today, we're going to use not only MEscope, and we'll look at some scripting that is a standard procedure, standard feature in MEscope. It comes with every package that you might own or that you might purchase. And when you write a script, it creates a hotkey. So the hotkey is just another command up on the toolbar, and you can press the hotkey and it will execute the script. So we're going to do some of that today. And then in addition, we're going to look at what's called our machinery monitoring package, and a specific part of that package called FACTS. Now, FACTS, if you spell it out, F-A-C-T-S, stands for Fault Correlation Tools. So we're going to get into using FACTS to, and it's a database search algorithm to identify different cases of machine unbalance from ODS data that we've extracted from a cell phone video. So quite a few different technologies here that I'm going to show you today. Last month, we went through the whole business of recording a cell phone video and post-processing it in MEscope. We have an option in there called, well, it's an option VES 9000, but it's called Video ODS. And so we've coined the term Video ODS as a way of extracting. It's an algorithm that extracts ODS data from a video, and a cell phone is the handiest device you have available for making a video. And then that ODS data, we animate the video with it and deform it so you can look at the video actually being slowed down and amplified in motion so you can see the vibration very clearly. And then we're going to go take that ODS data, archive it into a database, and use FACTS in a separate program, which is part of our machine maintenance package, that will search the database for the 10 best matches of ODS data with the current data that we log into the database. So we're going to go through all that today. That was quite a mouthful. Let's just go over an introduction here. The first 4 items in our outline, we pretty much covered last month, and I'm going to go through them very quickly again. But then we're going to talk about labeling and archiving order-based ODS data. So when we extracted an ODS from a video, and that in this case it's going to be labeled with a particular known unbalance of a rotating machine. We put that data into a database, and then FACS can identify any new ODS data that we put into the database. And if it doesn't match anything that we've labeled, then FACS will tell us that the probability of this being one of these conditions is very low. So we'll look at all that. This is a quick review. Why do we need vibration analysis? I always like to start off with this. I think I made this slide 40 years ago when I started in this business at an instrument company called Hewlett-Packard. They're no longer in the business, but they made low frequency vibration analyzers back then. The first three items have to do with called test and measurement, or let's say product development, new product development. And you know, the first one certainly has to do with cars, automobiles, modal analysis, ODS analysis. Vibration is certainly used to get the shakes and rattles out of cars. Difficult to control. It could be an airplane, a spaceship, whatever. If the vibration is interfering with the control mechanism in the machine, that's a problem. Too noisy. Women are very good at spotting noises in cars, especially. Us men are not as, we're more tolerant. The four items below: doesn't maintain tolerance, wears out too fast, fatigues prematurely, or breaks. These have to do more with machinery maintenance in a plant, in the field, a pumping network, whatever. Machine tools in a plant. So we're going to talk more about that. ODS analysis helps answer a number of questions. How much is it moving? And I don't have a definition of an ODS or an operating deflection shape here, but I'm assuming that you all understand that if I make two or more measurements on the surface of a machine or a structure, that's what constitutes an ODS. So the relative magnitude and phase between two or more points that I can measure on the surface of a running machine or a vibrating structure constitute an ODS. So we can answer a number of these questions, address them, and of course, mode shapes have to do with resonances. And so here's the next slide, and this is something I made up from 50 years of experience in this business. There's just four things that I've noticed about all mechanical vibration, and I've written them out as fundamental laws. Mass and elasticity are required in order for something to vibrate. And so that includes just about anything you can think of mechanically, or a bridge, or the earth itself. I'm living here in Southern California, and I've observed modes of vibration of the earth itself during an earthquake. So interesting stuff. Forces must be applied. So for something to vibrate, forces have to come from somewhere. And of course, in a rotating machine, there's all sorts of distributed forces that we call orders, which are multiples of the running speed of the machine, any rotating part. Resonances are excited at all frequencies. Now that's something that's not commonly understood. We'll talk about that a little bit more. And then vibration is a summation of mode shapes. So when we talk about modal analysis and we get into curve fitting to identify mode shapes from experimental data, that last one is the assumption behind what we're doing there. Okay, so here's a video ODS, and so why use a cell phone video? Well, all of you have one in your pocket, which has a camera in it, which is a high-speed video recording device. It's low cost, it's non-contacting, and you can make a video recording like the one that we're looking at here on the screen. And you can see that there's magnitude and phase of different parts of this machine that were recorded in the video, and then with our software, which we call Video ODS, we're animating this this frame of a video. Now, this happens to be sinusoidal, but if I do a sweep animation through the time records that we can extract from a video, then we see the overall motion of the machine. So here's an example of an ODS video that is being animated with a time-based ODS. We're sweeping through, and of course you don't see it here, but just the animation itself showing how this machine is vibrating, and it's certainly loose on its mounts. Now, we also resell a higher speed video camera for those that want to go up to a kilohertz or beyond. But we use the term frames per second. That's the sample rate of the camera in your cell phone. And there's 4 different sample rates in my iPhone: 30 frames per second, 60, 120, 240. So you can also say that's 30 hertz, 60 hertz, 120 hertz. So if you're using an analyzer, you typically talk in hertz or cycles per second. Frames per second is the same thing. When you convert that over to RPM of a rotating machine, you can record videos with machines that are running up to 7,200 RPM. Now, if the recording speed is 7,200 RPM, then the spectrum is typically half of that. Now, that's one of the restrictions, one of the rules of the fast Fourier transform. It's called Fmax, or the Nyquist frequency. However, in MEscope, we can, if we're just looking at orders, the video is going to capture orders up to 7,200 RPM, or multiples of the running speed. So if the machine's running at, well, any example, 1,800 RPM, we can actually see orders or peaks in our spectrum data up to 7,200 RPM. Now they're going to be aliased around 3,600 RPM, but we'll look at that in a minute. We can actually handle those aliased orders. Here's some other advantages for using a cell phone over a higher speed camera. You can actually record in dark places. So here's a video that was recorded of a machine in a dark room. You have a built-in camera, which is quite usable and bright in your cell phone. And the cell phones have algorithms in them which will enhance the video. And that technology is being improved all the time. So it's a remote device. You can use it on hot and dangerous machinery where you can't put accelerometers, or you could use a laser vibrometer, but again, very expensive. And if you use a high-speed camera, you typically have to use floodlights because there isn't enough time between frames at a kilohertz or higher for the photons to be measured by the camera. Most production machinery cannot be shut down. So if you're talking about a plant or a piping system or pumping system, operations people aren't going to allow you to shut things down. But you can measure what's called operating model analysis, and that is, or you can perform that while the machine is running. So that's very popular, and it's even used in the car industry today, driving a car around a track and so forth. Most vibration events occur too fast and the displacements are too small. So Video ODS allows you to slow down the animation between frames and increase the magnitude of the ODS vibration. We won't go into the details. We discussed a lot of that last week, and we'll look at a raw video here where we can see a little bit of the vibration, but by just playing the raw video. But most videos, you don't see a picture like this where it's been slowed down and magnified. Using your cell phone and a portable computer, a laptop, or an iPad in the field or in the plant, you can start looking at an animation like this and discover something like soft foot. Right there, you get a first look at the vibration. So it makes it more understandable to everybody, technicians, clients, plant management. You can show them a video like this and they understand the problem. Now with our software, we can actually choose points. There's a rectangular grid of points behind this frame of the video, behind all the frames actually. And we can select those points in MEscope and actually put up the vibration at a particular point on the animated picture. And in this case, you can see it's in inches per second. So it's in velocity, even though the data was recorded in displacement. So all videos record the vibration in displacement. And we'll talk a little more about that as we move on. So the ODS is extracted from a video because all the pixels in each frame are, quote, simultaneously sampled. Now, this is why we spend money for expensive analyzers, because if we're recording analog signals from accelerometers, we need simultaneous sampling or simultaneous acquisition of each of the signals from the accels. The advantage of a video is that each pixel is like an accelerometer. Now, in a cell phone, there's a slight delay from the recording of the pixels at the top of the screen versus the bottom, but the phase change between that and the time delay of recording those pixels is so small that we basically can assume that it's simultaneous. And we've done some work there, and you can't even see the difference with your eye between the top and bottom. MEscope extracts both time-based ODSs and frequency-based. So looking at things in the frequency domain has all the advantages that we use in modal analysis for curve fitting. Peaks in the spectrum are due to resonances or to orders, running speeds. Here's our experimental setup. And again, comparing ODS data to accelerometer data, we calculate something called an ODS FRF at Vibrant. Now, other people, we didn't discover this, but we found it's very useful for operating data because the magnitude of an ODS FRF is auto spectrum, and the phase is a phase between a vibration point, what we call a roving degree of freedom, and a reference point. So we have magnitude and phase of all these measurements, and we can differentiate the video-based time waveforms, TWFs, and get velocity units of our ODS FRFs. So we can extract the ODS data either by a cursor or by curve fitting. We won't get into that today. Maybe in the next month or after the holidays, we'll do some curve fitting of ODS FRFs, and I'll show you how we can extract mode shapes, well, ODS data and the mode shape perhaps dominating the ODS. Accelerometer data, we can integrate it in a frequency domain and get velocity units, so we can compare apples and apples. Now here's what I want to show you today, and that is our machinery monitoring software. Here's MEscope over here. Here's another program, an independent program called Console, and this is not even licensed. So you can have Console running on many different computers, your boss, your client, all the engineers or vibration analysts can be looking at data from a VTMax database. Now, VTMax is what we call the MEscope database. And it's a slightly different version. It's what we call machine-based. So we'll take a look at that. All right, here's what we're going to look at today. 9 different unbalanced cases. And we're going to run this machine. You can see there's a variable speed button here where I can vary the speed of the motor. The motor is behind this control box here, and then there's a belt that's connecting the motor to the rotor. So all the data is going to be taken with the rotor rotating at roughly 1,000 RPM. And we'll see that in our data here in a minute. And then what we do is, or what we did here for the 9 different videos that we took, where we put these screws, these unbalanced screws, in both the inboard and outboard rotor. And then we went ahead and made videos, extracted the time waveforms, calculated ODS FRFs, and saved the ODS at the running speed and 2 of the orders. So we'll go through all of that. First order, second, third order ODS, and then we'll use that data in facts to identify these different unbalanced cases. So that's what we're going to do here for the rest of this webinar. Okay, I've talked about ODS FRF. Here is a picture of the data, and we'll look at some of the live data in MEscope here in a minute. But this is what we extract from a video. And over here in the property spreadsheet, you can see that the DOFs are labeled with 3 different points, 1, 2, 3, 4, and then X and Y on each of the points, because that's what we get from the video, horizontal and vertical. The units are in inches. These are ODS FRFs, so they've already been calculated. We'll look at them in a minute. And they each have a measurement set associated with them. That's the number here in the square brackets. So what we're looking at here in this display is measurement set 3, and then number 4, number 5, and each measurement set has 4 measurements in it. 0.1 in the X and the Y, and 0.2 in the X and the Y. And those are 2 points on the top of the bearing blocks of the rotor kit. So that's where we're going to extract time waveforms from the videos. And I've already done all this. This is something we talked about last month. And then process that data in MEscope to calculate an ODS FRF like this, a whole set of them. So we're going to end up with 4 times 9, 36 measurement sets. You can see here's the last set down here from video number 9, and each of these videos was taken with a different unbalance screw or several screws screwed into the rotors. The other thing you can see here, here's the running speed, right around 1,000 RPM. This is the second order that's aliased around 1,800 RPM. So this data was taken at 60 frames per second with my cell phone. That translates into 3,600 RPM of a sampling frequency. And Fmax, or the Nyquist frequency, is half of that, because this data was processed using an FFT. So the second order is folding or aliased around 1,800 RPM. So if you do the math, the second order is at 2,000 RPM. That's 200 RPM above 1,800, and then that's, if you subtract that from 1,800, there it is, the second order folded at 1,600 RPM, round number. This is the third order. That is at 3,000 RPM, 3 times the running speed. That is what? Well, do the math. Subtract 1,800 from it, whatever that difference is, turn around and subtract that from 1,800 RPM, and you end up with something around 600 RPM. So that's what we can see in this data very clearly. Okay, let's talk about facts here for a minute. If I have a database of ODSs, in this case, the ODSs are just going to have, they're going to be 4 degrees of freedom, 0.1 in the X and Y, 0.2 in the X and Y, and those are on the bearing blocks. And then they're going to be labeled for each of the unbalanced cases. Save that data into a database, and then any new data that I archive into the database, FACS will identify it for me as one of these unbalanced cases. So we're going to go through that here in a minute. FACS is a search algorithm. It'll search all the data for a particular machine. Now I can have data for hundreds of machines in the database. And in a typical refinery, there might be thousands of motors and pumps that are being monitored with accelerometers now. So we could set up a health monitoring program using this software and using FACS. Over here is a picture, though, of what we get. FACS will lay out a bar chart of the 10 highest values of a FACS bar that it finds in the database, and for each of the ODSs, the first order, second order, third order ODS in this case, and then the 9 cases of unbalance that I've already logged into the database. So you can see how it orders them. And in this case, I pressed a hotkey that logged baseline data. Well, that's the unbalanced case. So we'll look at that. How does FACS work? Well, it has values between 0 and 1. A FACS value of 1 means that the 2 ODSs are identical. The one in the database that it found and the current data that I logged in. We use a rule of thumb. If it's greater than 90% or 0.9, the ODSs are similar. And if it's less than 0.9, then the ODSs are different. So how is it doing this calculation? It's something called in MEscope, again, this is unique to MEscope, a shape difference indicator. Now, most of you, if you do modal analysis or heard about it, you heard about something called MAC. And we also have that calculation in MEscope, modal assurance criterion. What MAC measures is the collinearity of 2 shapes. It could be a mode shape, it can be a operating deflection shape. So in this case, when we're taking machinery data off of a video, we could use MAC to tell us whether 2 ODSs are collinear or not. And this is kind of an example and a picture here showing a graph of between 2 shape values, and the shape values, shape A is 1 and 1, and shape B is X and Y. So this picture here is varying the X and Y and B, and then plotting the values of MAC. And you can see that all along this line here, when I plot up these values of MAC, the value is 1 when the shape A and B are collinear. So here's a top view over here. And again, you can see when they're collinear with one another, in other words, shape B is some multiple of 1 and 1, or a fraction of 1 and 1, then the value of MAC is going to be 1. When shape B is quite different than 1 and 1, the MAC value is 0. This is the calculation that we use in FACS, and this is also a standard property in MEscope with the signal processing software with that option. Again, same thing, we're going to take a shape of A of 1 and 1 and B of X and Y, but there's only 2 points. If I plot up A versus B for a number of values of X and Y of B, this is what the surface looks like, and there are only 2 points where SDI will equal to 1. And that is when B is equal to 1 and 1, or B is equal to -1 and -1. So same magnitude, opposite phase. And this is what we use in FACS to identify a machine unbalanced. Okay, so that's our last. Let's shut this down and go look at some other things. So I'm gonna get out of here and let's just put this down. Here's one of the videos. So I'll just play this for you very quickly. So here's a video that I took of the rotating machine, and we're simply going to take data from the top of each of the bearing blocks. Now, we also have taken data with this machine with accelerometer sitting on the top of the bearing block. So we've done that, and we have a video on our website that compares the accelerometer data with the video data in velocity units. So we can integrate one and differentiate the other. You can see here, the video is actually showing the unbalanced screws that I screwed into this outer rotor. And you can hear it. Now, we don't use the sound. We could use that in MEscope, but we don't use that. We're just going to use the vibration. And this is the case for 4 outer screws. So this was the most extreme case where I had 4 outer screws into the outer rotor. And you know, you can certainly see the pulley vibrating, but you can't see any other vibration of this machine from the raw video. When we process it in MEscope, you can see it very clearly. So let's just fire up MEscope here and look at some of this data. You can see my date code is last month. I don't even have a more recent version of MEscope here. So let me make this large, and we'll take a look. It's opening up all the files. I know I'm going very fast, so hopefully there'll be some answer or some questions that we can answer at the end of my presentation here. And you can go through the slides more carefully that I've already presented in the recording once we put it out on the website. Okay, so here is a video ODS FRF. So here's 4 of them for the case number 1. Now we looked at the data. Let me scroll all the way down. So in order to see this, there's many, case number 1 was the balance machine, or what we call baseline. Here they are listed up here with hotkeys. Now these are hotkeys, and we're going to look at hotkeys and scripts here in a minute, because I'm going to press these hotkeys, and then the hotkeys actually get access from console. So I can go to console and press these hotkeys remotely and execute a script. So we'll go through all that here in a minute. But what I first want to do is scroll down here to the bottom. Now you can see the 3 orders very clearly that I showed you in one of the previous PowerPoints. This is called a, well, let me just put this up. This is case number 9. You can see we're the Y direction, which is vertical on the machine, and X is horizontal on the bearing blocks, and this is point number 2. So this is the inboard bearing block. Let me put all 4 of them up here. So we'll change this format to strip chart, and we'll put up the 4 cases. Let me, this. So there is my data for point 1, which is the outboard bearing block in the vertical or in the horizontal and vertical. So there they are, and you can see the units are inches, very little motion. And then down here is point 2 in the X and 2 in the Y, the inboard, both in the vertical and horizontal. Horizontal first, vertical. So you can see the peaks, the 2 biggest peaks are the vertical direction of the rotor, because it's simply the machine is bouncing on some rubber mounts. Over here in the in the spreadsheet then are all the properties of my ODS FRFs, 36 different ODS FRFs for the 9 different unbalanced cases. So we went through all that last month. The first case here on measurement set number 1 was no screws attached. Number 2 was 1 screw attached to the outer rotor. And then number 3 was, I think, 1 screw on the inner rotor. But anyway, there are 9 different unbalanced cases where we used up to 4 screws on inner or outer rotor, and then the unbalanced. So now I'm going to press one of these hotkeys. So what this script will do, well, let's just take a look at the baseline, and they're all going to be the same. So I'm going to show you here, and what I did is I held down the control key so I can look at the script that gets executed when I press this hotkey. Now the first line here, and a script is just a spreadsheet of MEscope commands. So this is pretty simple. It says run another script. The VSL stands for Vibrant Script Language. Something called initialize, and run it 1 time. Then it says in this script, set a variable. And the variable is going to get set, and it's going to be a variable called measurement set. And the variable is going to be set to 1, which is our measurement set number 1. Then we're going to execute another script called acquire an event. So I would set this normally up if I were actually acquiring video data. I could set that up to acquire the video, but let's just go take a look at this script, because now what we're going to do is, since we already have extracted all the ODS FRFs and calculated them from the time waveforms that we extracted from the video, we're going to work in a data block here. So here's the format of a script. There's a window name. Well, we can have a script step here. This is a label for a various step. We've got 18 steps in this script. And so here's a window name, a command in that window, open a dialog. We're not going to open any dialog boxes. And then here's a description of what that command will do. So you can see I'm going to select no measurements, unselect all measurements, select measurements by spreadsheet property. Well, that was the property over here that was set to measurement set number 1. So if I come over here and execute that in this, see, this is the program. Very simple though. I'm sure some of you that are familiar with writing programs in Visual Basic or C# or anything else, the simplest way to write a program is kind of like this, a series of steps. So this is the way I can program MEscope to do automatic things, repeatable over and over and over again. So what this is going to do, select by measurement step. Well, the measurement step is down here, use a variable called measurement set, and it's going to use number 1. It's going to set up a cursor, and the cursor is going to be at the running speed around 1,000 RPM. It's saying, you know, use the x-axis units, which are RPM. So what it's going to be doing is processing data in this data block here. Well, let me just arrange things here a little better so we can see everything. Okay, so this script is working in this data block called 9 rotor unbalances. And it's going to set up a cursor, then it's going to save the ODS, save the shape, and it's going to save it into a shape table called archived SHP. Then it's going to come down here and do some other things. It's going to actually convert, now it's going to set the cursor to the aliased second order, which is around 2000 RPM. Okay, oh no, it's alias. It's not 2000 RPM. It's alias around 1800, so it's around 1600 RPM. Remember, we subtract the order frequency from 1800 and then take that difference and subtract that from 1800. So that's where we get to 1600. So now it's going to go in and grab and save the ODS for the second order. And then finally, it's going to set the cursor. This is the peak cursor at 600 RPM and save the ODS there. Now it's going to convert the frequencies in this spreadsheet called, and these are the corrections of the frequencies. We don't want to save the alias. We want to save the actual order frequency. And then down here, we're going to differentiate the data. So we can differentiate either the ODS FRF data directly, sometimes we do that, or we can differentiate the shape data from inches to velocity. So what we're going to do is actually save ODS data in velocity units, and then this last step, MEscope, archive the shape data into save and archive video ODS unbalances. So there's a shape table called video ODS unbalances. Let me go show that one to you. Oh, that's the machine name. That's not the. So what I need to do is go to the machine definition. Okay, so let's go take a quick look at that. Machine setup. So here's what is being archived. I can archive this is my latest grid model. Remember I told you that we can, and what that looks like, let's just go look at a grid model. That's just a picture of the machine that we took right off of the video. So there's the model that goes into the database. And if I display the grid, let's just show the points. So there they are. So last month we went into all the details of these are the visible points that we pulled off of the video. All the background points we're not interested in, so those aren't part of our analysis. Okay, let's go ahead and just move along. This is my machine definition. You can see down here my archived monitor shape table. To go into the database is a shape called archived shape. That's what's going to go into the MEscope database, the archival database, or the machine-based database for this machine. So let me just go ahead and I'm going to put all this stuff down here. Let's go back to Windows, and we'll minimize all the windows. And I'm going to go up here and let me just press baseline ODS. Okay, it says no archive database connection. Do you want to continue? I'll say no. Okay, so it stopped the script down here on this last line because it can't archive anything. Why not? Well, I haven't connected MEscope to the database. So here I just clicked on a command over here called database connection. Archived, here it is. This is the database. It's got a different acronym on it, but I'm going to go ahead and connect. So now I'm connected to the database. And if I go ahead and hit this hotkey again, there it is. Now that script, you can see it corrected the frequencies. I've got the orders at their correct frequencies, and I've got the ODS data in velocity. We talked about all that. The script did all that for me. And then here's the magnitude and phase of those three ODS FRFs, or the 3 ODSs that we extracted from ODS FRF. And you can see these don't look very interesting because the machine was balanced. There were no unbalanced weights. Let's go out here and hit 4 outer screws. Here's a severe unbalanced case. So I'm just going to hit that. Okay, so bingo, there it is. You can see that the running speed is very large. The other orders are not so large though compared to the running speed, the first order, very large. But here's the data over here in the shape table and the correct frequencies. So MEscope is doing this. So let's just put this down for a minute and let's go start console. How are we doing on time? Almost done. Okay, so here's console, a second program that is part of the machine monitoring package. It's another package that you can order with MEscope that goes along with, you may already own MEscope, and then you can order the option for machinery monitoring, and that gives you this new database and this new software for actually monitoring the health of machines or whatever you want to acquire, either with accelerometers or okay, let's go back and look at the machine gallery. So here it is. I've already opened up this machine in the database when I ran the hotkey in MEscope, and you can see I got another one in here for STM MIMO. That's going to be our topic in January. Both of these are subject of IMAC papers that are also available on our website now. So we go into a lot more details and discussion of what I'm showing you here today. So where do we want to go from here? Let's just go right to facts and see what's in there. So I'm going to show a fax. Well, here is the fax bar, and you can see that console has already identified the last hotkey that I pressed in MEscope, and it's identified the data that was archived in the database as 4 outer screws. Now, the next closest fax bar is 2 outer screws. Now remember, these bars are what we call the shape difference indicator. So the shape difference indicator went into the database, looked at all the data that was archived in there, and said the closest match to the data that you just pushed in was 4 outer screws, that unbalanced case. And then here's the first, second, and third order. So they're all doing a real good job of identifying. But you can see the first order and the third order are identifying this unbalanced case also. Second order, not so much. And when we looked at the peaks in the ODS FRF, they were very small for this case. Okay, so how does it know that? Well, let's look at something else called the event log. So here's the event log. So when I first archive data into the database, you can see that these events are operator events that I identified as the 4 screws, 3 screws, inner screws. These are the 9 unbalanced cases that I logged into the database, and then I labeled that data, each of those sets of ODS data, as one of the unbalanced cases. So whenever I put some more data into the database, fax will identify one of those cases. Now this is very flexible software. We can set up warning levels on what we call gauges. Let's just go look at some of the gauges. Here's the gauges. You can see they're all in the red because they were set up with the baseline. Now I can set those gauges to different levels, anything I like. You can see there's a gauge for each of, here's the outboard horizontal, vertical, inboard, horizontal, vertical. I can label those differently. You know, all that information is here in the spreadsheet. So I can go into here and just label all kinds of things. There's first order. Well, let's just go back and look at facts, because that's I'm gonna clear out all these and just go back here and let's just look at facts. Got a little bit of a problem here, Mark. Facts. Okay. And here's all the hotkeys. So console has the same hotkeys here that are in MEscope, that I created in MEscope to execute different scripts. So if I press a hotkey here, really all I need to do to monitor data, you know, and I can acquire data with MEscope. I can set up scripts to do curve fitting, and in this case, we just save the data at the. Let me just press one of these. Here's 3 outer screws, and let's just see what happens when I press that hotkey. Well, it's going to it went back to MEscope because MEscope was connected to the database. It knew that, and bingo, it identified that unbalanced case. And again, all 3 orders identified it, and the 3rd order actually came close to, but see, it's only 84%, so it's less than 90%. But the 3rd order kind of said this could be, it's 84% like the baseline case, which is no screw at all. Let's go back to baseline and just press that and see what that looks like. Okay, it identified the baseline, and I'm going to rotate this around. So baseline is clearly quite different than any of the unbalanced cases where we added screws. The closest one is the 4 outer balance screws, but those aren't even close. I mean, this is like 60%. This one over here is 30%. So, you know, we're using SDI in facts to identify these cases. Let's just try one more. 4 inner screws. That's a lot of unbalance near the pulley location. Okay, facts identified it. There it is, 4 inner screws, and it's a little bit like the 2 inner screw case, but only 73% alike. So it's giving us a very good quantitative picture of each of these unbalanced cases and how much they look like events that have already been logged into the database. So you can see how, as I log more events in and identify them and label the data, I can monitor more and more machine faults with this algorithm and with this software. Mark, I'm going to wrap it up there and ask if there's any questions.
Nothing yet. Anybody have any questions? Feel free to type those in there in the question box.
I know we covered a lot. You can go check out the IMAC papers on our website. I think I have a copy of the one that we used here today. This is paper number 80. So using a cell phone, and facts is another term we're using for facts is called ODS correlation. And again, facts is using our SDI calculation, which is a correlation coefficient between 2 shapes. They can be mode shapes, they can be ODSs. and it has values between 0 and 1. So that's the correlation coefficient that FACS is using to identify machine faults. And in this case, we used it just to diagnose unbalanced cases. And by diagnose, we already identified or labeled the ODS data for these unbalanced cases. So when we took videos of the machine with the different unbalanced cases, here's a review of the first order and the alias second and third order. Oh, and then I didn't show you this. This is a trend plot. Well, let's go look at that real quick in console, because we didn't look at the trend plot. That's where we can just see all the data trended. Let me go to home, trend plot. Okay, so here's a bar chart. Now it's just showing the last 10 minutes. If I show all, there's all the data that's been put into the database. You can see Monday, Sunday, Thursday. This is the bar chart. I can go change, let's just go make it look like, let's see, charting. We'll go back and look at just a line chart. Okay, so there it is. There's the line chart of the data that we put into the database. And again, if I go back and hit one of these hotkeys, I don't know, let's just hit 2 outer screws and see what the values look like. Okay, so there it is. There are the 4 values of the ODS that came in. And so I can compare those with, you can see these low levels here are, and these are all in inches per second. So I can just go see that, you know, wherever there's a high level of vibration, the high level would be the 4 outer screws. Let's put that back in again. And that will show me a higher level of vibration. Oh yeah, you can see it here, quite a bit higher with the Y values. Let's see, are these labeled? Can I, yeah, these are 2X and 2Y. So here's a very high level, up almost a 1/10 of an inch per second with that unbalanced screw. Okay.
We got a few questions popping in here now.
Oh, good.
Skip Williams is asking, are the screws in phase from inbound to outbound?
We can look at phases now. We've been looking at just at magnitudes here, and of course in this tech paper we're just using FACS. FACS does look at magnitude and phase. So if the magnitudes are the same and the phases are different, the FACS value will drop down. So remember, well, let me just get this back up here. See if we've got it here. Scroll all the way down here and take a look. FACS is using SDI, and SDI, now this is just showing magnitudes, but it also shows the phase being the 2 points where FACS is the same, or SDI has the same value, is plus or minus 1 in this case. So, but any other phase value, you can see that when the values are any other value other than plus or minus 1, the SDI value, and therefore FACS, drops down closer to 0. So as soon as we get away from the value of the archived shape in the shape database, FACS is going to drop down. So yes, it is very sensitive to phases, and that's a common thing that we look for in machinery maintenance. For instance, a phase difference between motor and pump would indicate misalignment. We should do a whole video on that, or a whole webinar on that. So thanks for that question. We'll do that in the future, and we'll look at phase difference. Go back to
question.
Go ahead.
Oh, okay, just one more question. I'm an experienced user of modal analysis, but your method seems to be complicated. Is there a way to make your analysis easier? Maybe he's referring to FACS is a little bit complicated.
FACS works with mode shapes, just like Mac works with mode shapes. We're going to get into modal analysis and machinery monitoring again. We've been doing a whole series with video ODS and cell phone videos, so we're not spending time on modal analysis as much. In the next webinar, I will curve fit some OMA data. In other words, the data we get off of a video is, and if we go ahead and curve fit it and do modal on it, then we call that OMA. Now, typically that's done with accelerometers, but we can do it with video or accelerometers, either one. We happen to be working with this rotor kit and showing that, but good suggestion. We should do another webinar. Maybe I'll write these two down. We'll do one on phase differences. You can see these ODSs have different phases in them. So FACS is considering the magnitude and the phase, and they can be arbitrary. Modal, we can curve fit this data, the ODS FRF data, and I mean, a more common measurement we make with OMA data, which we can extract from video, is a cross spectrum. So again, we use a reference and we compute a cross spectrum between a reference and a roving sensor. In this case, it would be a video, but it could be accelerometers. And we curve fit that data. We can't measure FRFs unless we shut the machine off and measure the force impact. Now, there are different tricks you can use with impacting. You can do random impacting. You can put a shaker on a machine while it's running and do a lot of spectrum averaging to get rid of, the internal forces. But a true modal requires that you measure the force and the response and compute what we call an FRF. ODS FRF is from operating data only, or output only data. But good questions. Any other ones, Mark?
Not at this time, no. I believe we can wrap her up.
It's difficult to cover many of the details in a 1-hour webinar like this. So I recommend you go read the IMAC paper, and of course you can look at these videos and, scratch your head and think about them a little bit more, or the PowerPoints from the video. But good suggestions. We have a question and answer area on our website. That's also another place where you can get some questions answered, and we're going to expand that more in the future also. All right, well, let's just wrap it up then.
Yeah, we'll leave it there. And we thank you all for joining us. Those of you that are in the States, we wish you all a very happy Thanksgiving next week. And we'll probably be skipping a webinar in December just due to the holidays. So be sure to join us in January. We'll get another webinar ramped up. And we will get this webinar here recorded and up on our YouTube site sometime next week. So look out for that. And as always, if you have any questions, feel free to send your questions into sales@vivetech.com, and we'll get those questions answered for you. With that, we'll let everybody go, and have a great weekend, everybody. We'll talk to you soon.
Okay.